Okay, so last thing we're going to look at this week is 11.3, which is on the binomial theorem. And this really relates to summations, adding things up. And you'll see what I mean. So we're going to look at a couple special examples of a series. Specifically, taking a binomial and raising it to a power, like that. If you take a plus b and you square it, remember that means a plus b times a plus b. So you have to FOIL it. And you get a squared plus 2ab plus b squared. Now, if you took that, a squared plus 2ab b plus b squared, and then you multiplied that by a plus b again, what would that basically give you? I mean, you don't have to do it out. But multiplying this by another copy of a plus b would give me
trinomial.
A what? A triangle?
Trinomial.
Oh, a trinomial. I said a tri. So this is a trinomial right now because it has 3 terms. I'm kind of thinking like, what would be right? What do you think would be right here if I continued this pattern by multiplying by another copy of a plus b?
It's another exponent.
What would the exponent be?
B to the third.
To the third. So if you do a plus b squared, which is right here, and multiply by another copy of a plus b, I'm not going to do it all out, but if you did, by FOILing it, you would get that. A cubed plus 3a squared b plus 3ab squared plus b cubed. Now I'm going to do it again. If I multiplied by a plus b another time and FOILed it to that, I would get that. What I want to start to look for here is patterns. What's happening? How many terms do I get when I do it? What's happening to the exponents on the a's? What's happening to the exponents on the b's? There's some patterns. What about the coefficients? 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. The next one would be 1, 5, 10, 10, 5, 1. Those would be your coefficients if you multiplied it to the 5th power. 1, 5, 10, 10, 5, 1. These numbers are also coming from somewhere. So I basically want a quick way to be able to do that without FOILing it out. Like if I said a plus b to the 12th power, we don't want to write a plus b times a plus b 12 times in FOIL. That's going to be a mess. So there's lots of patterns that happen here. Does anybody see a connection between how many terms you end up with and the power you were raising to? Yep.
The exponent plus 1 is the amount of terms.
Yep. If you square, as Nick said earlier, you get 3. You get a trinomial. If you raise to the 4th power, 1, 2, 3, 4, 5 terms. So whatever power you're using for your exponent here, you get 1 more in terms of how many terms you get. Does anybody notice any other patterns? Yeah?
It's like your weird triangle thing you showed a while ago, where like the 1a4 plus the 4a, those two.
The triangle thing?
Coefficients, yeah, it makes
Yeah.
you walk down.
So yep, this is Pascal's triangle. If you remember, we'll put this up in a second, but we may have looked at this a little while ago when we talked about the Fibonacci sequence. We looked at something on diagonals. But if you write out the rows of Pascal's triangle, each number is the sum of the 2 above it, and there's 1s on the outside. If you want to raise something to the 3rd power, if you go to row 3, 1, 3, 3, 1. Let's go back and look at what happened when we raised to the 3rd power. 1, 3, 3, 1. So these exponents, or these coefficients, are coming from Pascal's triangle. Okay, so that's a good pattern to notice with the numbers. How about the letters? What do you notice in the pattern with the A's and the B's as you read from left to right? John?
a's decrease as you go right, and the exponent for the b's increase as you go right.
Yep. So whatever you put here, you start with that to the highest power, or the power you started with. And then it goes down, a to the fourth, a to the third, a to the second, a. Technically the last one is a to the 0, but anything to the 0 power is what? 1. So we don't write that. And the b's are just the opposite. You start with b, technically to the 0 power, and then you do b to the first, second, third, fourth, fifth. So the a's are going down 1 until they disappear. The b's are going up 1, starting with 0, so you don't have to write the first one. And the coefficients are coming from Pascal's triangle. So those are pretty much the patterns, and if we understand those patterns, we can expand a plus b to any power very quickly. The only kind of trick here is that the coefficients come from Pascal's triangle. So what if you wanted to do a plus b to the 20th? Technically that would mean you need to know row 20 in this triangle, which that could be kind of annoying to figure out. So as long as this exponent isn't too big, I would say 7 or 8, even 9, that's not too bad, we can do it. So I think we noticed all these patterns. In the expansion, you always have one more term than the exponent you were using. Nobody saw this one. The sum of the exponents is n. So that's a 5. 4 plus 1 is 5. 3 plus 2 is 5. 2 plus 3, 4 plus 1, and 5. The sums of all the exponents on the terms for each term comes out to 5. But I think we've noticed every other pattern. The degree of A goes down, the degree of B goes up. And where are the coefficients coming from? Pascal's triangle, we already saw that.
Did you just pull Pascal's triangle?
Yep, I'll put Pascal's triangle back up. So the coefficients come from this triangle. Each row begins and ends with a 1. There's also symmetry in the triangle. So once you write the first half of the row, the second half is it's like a mirror image. 1, 4, 6, and then it's going to repeat 4, 1. 1, 5, 10, 10, 5, 1. Also, kind of a weird little fact, but if you look at prime rows, every number in that row is a multiple of that row number. So like row 3 is a prime. Row 3 is a prime. If you look at row 3, the numbers inside the triangle, you always have 1s on the outside, but the numbers on the inside are all multiples of 3. The next prime number is 5. All the numbers in that row are multiples of 5. The next prime number after 5 would be 7. Well, if you found the next row, this would be a 1, this would be a 7, that's a 21, that's a 35, and so on. All the numbers in row 7 are multiples of 7. Just the pattern, the way it works. Not true for rows that are not prime. Every number in this row is not a multiple of 4, because you have 6. But 4 is not prime. Each entry is the sum of the two numbers above it. And the numbers in the nth row give you the coefficients in the expansion of a plus b to the n. Very important, you start counting with row 0. Okay. This is row 0, this is row 1, this is row 2. And when we talk about columns, we also start with column 0. So if you were looking at this number, that number is in row 4, column 1, 0, 1. That number is in row 5, column 0, 1, 2, 3. That's row 5, column 3. And we're going to see a notation we use to describe that position like this, eventually. That's the notation that means the number in row 5, column 3. Row, column. I'll talk more about that later. That's just a notation. Right, so let's try a plus b to the 6th. Let's start with the variable. What's the power on a going to be first?
6.
6. And the power on b? 0, so it's not even there. What's the next power on A? 5. Power on B? 1. Leave a little room because you got to put the coefficient in there. What's the next power on A? B? 2. Next power on A and B? 3. Next one? 2, 4. Okay, let's go down here. A, B. Next one? 1, 5. And the last one?
B6.
Just B to the 6. No, A to the 0. Okay. So we've got the letters with the proper exponents. Now we have to put in the coefficients. The coefficients are going to come from row 6. So do we have row 6? Yep. So 1, 6, 15, 20, and then it repeats from there. So 1, 6, 15, 20. 1, 6, 15, 20, 15, 6, 1. And that's a quick way to take A plus B and raise it to the 6th power without having to FOIL or do any of that. Any questions on that? All right, so you put whatever you have here as your first one with the highest exponent, and whatever you have here starts with the lowest exponent. Even if it's something a little more complicated. You put whatever you have here, 2x, to your highest power. So what's our highest power going to be in this case? 4. And what's going to be the power on y in the first term? 0, so we don't write it. Leave a little bit of space because we're going to fill in the coefficients. I can just put boxes around them so we remember to do it. So coefficient's going to go here. Then we're going to have 2x to the y. And y to the first plus 2x to the second, y to the second, plus 2x to the first, y to the third, plus, now it's 2x to the 0, so we don't write that, y to the fourth. Now, go to row 4, get your coefficients. 1, 4, 6, 4, 1. 1, 4, 6, 4, 1. Now, this one has a little bit of simplifying you need to do. Okay? When you have a product raised to a power, you raise each factor in that product to the power. And then we have to multiply by the number that's in front. So what's 2 to the 4th power? 16 times 1. And then what's x to that power? X to the 4th. Now do this one. What's 2 to the 3rd power? 8 times 4. 32. And then x to that power? X to the 3rd, y to the 1st. All right. Now we have 2x squared. What's 2 to the 2nd power?
4.
Times 6.
24.
So we have 24. X to what power? Squared. Y to what power? Squared. This. All right. Let's see. 1, 2. We did the 3rd one. Okay. 4th one. What's 2 to the 1st power? 2 times 4. 8. X to the 1st power? X. Y cubed. And the last one, well, it's just 1 y to the 4th. Okay, so on that one, there's a little bit of simplifying you had to do because you had a product raised to a power. Any question on that one? All right, let's try this one. So to the third, and this is our first one. This is our second one. So what's going to be the first thing we write down? Well, we'll have a coefficient. We'll go back and look that up in a minute.
Third.
What goes here?
X to the third. Or 2x to the third.
2x to the third. And then the next one is the y squared. And what power does y squared get raised to first?
Y6. Or
Just to
no.
To the 0. So we don't write it. Next one. What's the 2x going to get raised to this time? Second. And what's the y squared going to get raised to?
1.
1. All right, next one. What's the 2x going to have as its exponent? 1. And what's the y squared going to have for its exponent?
4.
Well, y squared to the second. We'll simplify that. And the last one, the 2x, what's that going to have as an exponent? So that's gone. And what about the y to the second? To the third. Okay, now fill in your coefficients. What are the coefficients in row 3?
1, 3, 3.
Nope. In any arithmetic there that we can do out, we need to do that. Okay, so what's this first term going to become?
8x to the third.
Yep, 8x to the third. What's going to be the x term in the next one?
X squared.
24. X squared.
2 to the second is how much?
Oh,
4 times 3. 12x to the second. Y to the
second.
second. Okay, next one. What's my x term going to be?
6x.
6x. And what about my y term? Y squared squared.
Y to the 4th.
Yep, y to the 4th. And then my last term, y to the 6th. Okay, so that's a quick way, again, just to FOIL out or raise a binomial, which means you have something plus something in parentheses, to a power. Now, if it was something minus something, I'm not going to go through how to do this whole thing, but what I've taught you right now only works when it's addition. So how could you rewrite what's inside here as an addition problem?
3x plus -2y.
There you go. So now, in terms of like this first one we did, the a and the b, this is your a, this whole thing is your b, -2y. So what's going to happen when you have a negative, depending on the power you raise it to, if you raise it to an even, the negative is going to disappear. If you raise it to an odd, it's going to stay. So when you simplify this whole thing, because of that negative, instead of being a plus sign every time, it's going to alternate. Plus, minus, plus, minus, plus, minus. The minus will cancel on all the even powers, and it will remain on all the odd powers. Any question on that idea? Okay, but it's still the same idea. So again, fine if n is small, but what if n is large? We need a better way to calculate binomial coefficients. Okay, like the 1331, 14641. Those are binomial coefficients. We can't rely on Pascal's triangle, especially if I said to you something like this. Now, I wouldn't have you do out an entire problem like this on the test, But I might ask you something like, what would be the coefficient of the a to the 40th, b to the 20th term? Because we know that that term is going to come up somewhere. These two exponents always add up to 60. And you will have a time when you get down to 40 for a, and you get up to the 20th power for b. And I would want to know what number goes right there. Just one number. There's a way to figure out that number. Technically, you need to go to row 40, column 20 in Pascal's triangle. That's what you need to find. But writing out Pascal's triangle to 40 rows, not the way to do it. So, the way you can figure out any particular number in the triangle without doing it out is with what's called a factorial. And the symbol for factorial is that. Has anyone ever seen an exclamation point used in math?
Yes.
No? Some people yes, no. Right. So basically what a factorial means, if I write one out, I think you'll understand it very easily. If I asked you to do 5 factorial, it means to do this. You multiply every number from 1 up to that number. So 6 factorial is 1 times 2 times 3 times 4 times 5 times 6. So it's the product of every integer from 1 up to your number. So for any positive integer, n, the symbol for a factorial is this. N! And you have to say it that way because it's got an exclamation point. So I mean, if you just say n, then I'm going to think you're talking about this. But then if you say n, I'm really excited, I know what you're talking about. So n factorial, n exclamation point, means to do this in general. Multiply every number from 1 up to your number. Factorial is only defined for integers. There is a such thing as doing things like 3.5 factorial, but that gets way beyond what we're going to do. It's kind of different. It's very different. So it gets into using pi and other things. So we're only going to worry about doing a factorial with an integer. Okay, so again, n factorial, product of all the integers from 1 up to n. So let's try a couple. 0 factorial, that's kind of a special case. 0 factorial is defined to be 1. How about 1 factorial? The product of every number from 1 to 1. 1. How about 2 factorial?
2.
3 factorial? 6. 4 factorial? 24. And what about 5 factorial?
96.
120. Factorials grow extremely quick. By the time you get to around, I think it's 65 factorial, you can no longer do it on the calculator. That'd be 65 times 64 times 63 all the way down to 1. If you press math and you go to probability, the 4th option down is an exclamation point. And I can still do 65 factorial. Once this number goes over 99, then you're done. The calculator can't do it anymore. Because this means in scientific notation, 8.2 times 10 to the 90th power. And the exponent in scientific notation on a graphing calculator can only be up to 2 digits. So I forget where the cutoff is. It's probably in the 70s somewhere that you can no longer do the factorial on the calculator. So factorials are going to help us to be able to find the binomial coefficients. So I told you there's a notation that we're going to use. If you want to find something in a certain row and in a certain column, the notation that we're going to use is n on top of r with parentheses around it. not how you say it, but I'll tell you how you say it in a second. That's pronounced N choose R. And the reason it's pronounced N choose R is because this is a probability concept. If I had 3 objects that I was holding, and I said to you, you can choose any 2 that you want, and you can keep them. How many ways can you choose 2 of these objects to keep? Well, there's 3 ways to do it. You could choose the dry erase and the Sharpie. You could take the smartboard pen and the dry erase. Or you could take the Sharpie and the smartboard pen. Right? There's 3 objects. There's 3 ways you can pick 2 of them. The order you pick them in doesn't matter. Like if you're going home with the Sharpie and the smartboard pen, at the end of the day, it doesn't matter if you pick the Sharpie first or you pick the smartboard pen. The order doesn't matter. Just these are the 2 objects you decided to take out of the 3 you could pick from. So if you go to row 3, column 2 in Pascal's triangle, 0, 1, 2, row 3, column 2 tells you there were 3 ways to do it. If you went to row 5, column 3, that would be a probability, like saying I have 5 objects you can pick from. You can take any 3 that you want. How many different ways can you choose 3 objects out of 5? Well, if you went to the triangle, and you went to row 5, column 3, row 5, column 0, 1, 2, 3. There are 10 different ways that you could choose 3 objects out of a group of 5. Right? So that's where the notation comes from. So Pascal's triangle has a lot to do with probability as well. Remember, when you're talking about N choose R, you're always talking about starting with the 0 column and 0 row. Pascal's triangle does not start with row 1. It starts with row 0, row 1, row 2, row 3. Same with the columns. Column 0, 1, 2, 3.
And in the N choose R columns on the top?
Yep. In N choose R, no, rows on the top. No, row, column. So the row is N, the column is R. The row you want, the column you want. And there is a formula with factorials to calculate directly anything you want to know. If I want to know this, I can find it. Row 30, column 12. Easy. That's the formula. So the formula is n factorial divided by n minus r factorial times r factorial. This is the formula if you study probability in the future. This is the formula for what's called a combination. There's 2 types of things in probability, combinations and permutations. We're basically doing combinations. So here's Pascal's triangle, written out by describing the position of each term, not the term itself. So the very top spot in Pascal's triangle is called row 0, column 0. The next row would be written with this notation. Row 1, column 0, row 1, column 1. The next row 2, column 0, row 2, column 1, row 2, column 2. Row 3, column 0, 3, column 1, 3, column 2, row 3, column 3. So this is how you write Pascal's triangle using that N choose R notation. So we'll try it for different ones, but if you plug in the row here and the column here, you will get any one of the numbers that we've already done in the triangle automatically. Still, not a fast way if you had to find every number in like row 50. Well, that's a lot of numbers. You'd have to use this formula 50 times to do it. but you could, or you could have a computer do it. All right, so any questions on that? Yep.
So how deep does this go in this task? Like, is this like a very prevalent subject, or is it just like, oh, I know what Pascal's triangle is, and I can like factor a binomial?
You need to know more than you need to know this one. Because in a minute we're going to do something like this.
Yeah, for sure.
Row 9, in fact on the test, I think I asked you for something in row 20 or 30. So maybe it's even row 70.
So it's just finding the coefficients, though. It's not factoring out the complete, like.
Yeah.
Okay.
So we're going to get to doing this in 1 second.
Yeah.
So here is your binomial theorem, written out now using the n choose r notation. So remember, you start with, well, what does this tell you? N, that tells you the what in Pascal's triangle? The row. So remember, row is on top, column is in the bottom. What's the first column you always start with? 0. So to get the first coefficient in this expansion, you go to the row you need to, and you start with column 0. And you're going to have a to what power? N. A to the highest power. What about b? 0. B's not there yet. So you go to the next term. The next coefficient is going to be from row n, but now we're going to go to column what? We're going to go to the next column. So row n, column 1. What's going to happen to the exponent on the a?
N minus 1.
It's going to drop down 1. Right? It's going to go down 1. The exponent on the b is going to go up 1. Then we need the next coefficient. Everything is from row n. But now we're going to go to column 2. You're going to drop the exponent on the a again. You're going to increase the exponent on the b. And you're going to keep going till finally you get to the second to last term. You know you're at the last term when these two numbers are the same. Okay? When you get to the second to last term, this number, the column you're at, will be 1 less than your row. You're almost at the end of your row. You're 1 before. The exponent on the a, this is the last time you see it. It's now a to the first power. It's dropped all the way down to 1. And b is almost at the highest power. It's 1 less than the highest power. And then your last term, now you're finally in the same row and column. That's the end. Row 3, column 3, all the way on the right. The exponent on the a has dropped to a 0, and the exponent on the b has increased to its maximum, which is n. So it's a little confusing to write it generically, but it's the same pattern you've been doing. I'm just trying to show you that these numbers in front now are not going to be calculated with Pascal's triangle. We can calculate them with that formula. Right, so what I want to do is just practice calculating a couple binomial coefficients, and then you'll see what we do from there. So you're definitely going to have something like that on the test.
Can you go back to the formula real quick? No, the other one.
Oh, the n factorial
Yeah, thank you.
over n minus r factorial, r factorial. Now remember, I said factorials get really big. So the problem is going to be, if I gave you something in like row 70 or 80, your calculator can't do it if you just type it in like this. It won't work. Calculator will say error overflow because it's too big. So I need to show you a way that you can make it smaller before you type it in. And I'll show you what happens. Now, first of all, think about if you have a certain number of objects, I think it's the easiest way to think of it, and you're choosing R of them, like 3 choose 2. The number of choices that you can make is always what kind of number?
Integer.
It's always an integer. You never get a decimal. There's not 3.5 ways to choose objects from it. Right? You could have 3 ways or 4 ways. There's not 3.5 ways. So this is always going to result in an integer. If something is an integer, then that means every number in the denominator divides into the numerator evenly, always. If it didn't, you'd be left with a denominator, which means you have a fraction, which means you don't have an integer. So the denominator will always divide into the numerator. And that's how we're going to reduce it before typing it in. All right, so let's try. What's n in this case?
6.
6, and what's r?
4.
4. So to figure this out, what goes in the top? 6 factorial. Don't worry about doing it out right now. What's going to go inside those parentheses?
6 minus 4. 6 minus 4.
Factorial. What's 6 minus 4?
2.
So that's 2 factorial. And what goes next to it?
4 factorial.
4 factorial. Now, you always want to write out, at least to start, write out the biggest one. So let's write out the, you know what, we'll write anything now. Just let's expand it all. So 6 factorial means 6 times 5 times 4 times 3 times 2. That's 2 factorial. And then 4 factorial is 4, 3, 2. What do you see like a big chunk of stuff that cancels out? That's in the top and the bottom. 4, 3, 2. You can always cancel the bigger factorial in the bottom completely into the one in the top from its point down. So you have a 4, 3, 2. So everything from there down will cancel with the 4, 3, 2 in the bottom. Now, the 2 goes into 6 3 times, and what do you get for an answer? 15. So even though 6 factorial is a pretty big number, 700 something, I think, you didn't really have to deal with it because you were able to reduce it first. Right. Let's try this one. What would go on top?
9 factorial.
9 factorial. And in the bottom?
4 factorial.
4 factorial.
9 factorial.
And what goes here?
5 factorial.
5 factorial. So if you were to write out the top, everything from what number down is going to be gone? 5. Because you have a 5, 4, 3, 2 in the bottom, and you're going to have a 5, 4, 3, 2 when you write out 9 factorial. So all you have to do is write 9, 8, 7, 6. The 5, 4, 3, 2 is going to cancel with 5 factorial. And 4 factorial, 4 times 3 times 2. Okay, what can you cancel here? 4 cancels into 8 how many times?
Twice.
Twice. Okay, what can you cancel now?
3 into 9.
You can do it that way. 3 goes into 9 how many times?
3.
And what
And
else?
then 2 into 6.
Yep. So 2 goes into itself. 3. So your denominator is a 1. It always will be. And you're left with 3 times 2 times 7 times 3. Well, what's 3 times 2? 6. 6 times 7.
40.
And what's 42 times 3?
126.
42 times 3 is, 126. Okay, so if you go back and look at like, what is 9 factorial? That's a pretty big number, I think it's in the thousands. Yeah, it's 362,880. But you didn't have to deal with a number in the hundreds of thousands at all. You just had to deal with 3 times 2 times 7 times 3 because of the way we reduced it. Questions on doing now? Try. Last one. So now, this is where I'm not going to ask you to do the whole thing out. All I want to know is if you did do the whole thing out, tell me the 12th term of this expansion. So what I like to do is set up a diagram for this. When you expand something to the 15th power, how many terms are you going to end up with? 16. You end up with one more. So you're going to get 16 different terms. And you could number them. We don't need to number them all. And the reason I started numbering with the 0th term and not the first term is because of the way Pascal's triangle works. It starts with row 0, column 0. So if you don't start with the 0th term, you're going to be off by 1. So when you're trying to figure out the 12th term, number them like this. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's the one that I want to know right there. So let's start with our two things that are here first, and then we'll figure out the binomial coefficient at the end. Okay, so you're going to have some binomial coefficient, which we're going to figure out. You're going to have a 2x to a certain power, and you're going to have a 3y to a certain power. When you add the two powers together, what are they going to add up to?
15.
They're going to add to 15. So just work your way over to that term. This would be 2x to the what power? 15. Next one. 14.
13.
12, 11, 10,
4, 8, 7, 6, 5, 4, 3.
Three.
Second counting 3.
So that's going to be 2x to the third, and it's going to be 3y to the 12th. You can always check it by, I guess you could work backwards too, because you're closer to this end. That might be easier. This is going to be 3y to the 15th, 14th, 13th, 12th. Actually, that probably would have been better to work that way. But we got that. So we do have to do this out. We'll come back to that. Now we need to figure this out. What's the notation for what's going to go right there? What row do we want to look in?
12.
Well, if we were doing row 3 of Pascal's triangle, we could just do that by hand.
15.
We want to go to the 15th row. And what column do we want to be in?
12.
Yeah. So this would be column 0, 1, 2, 3, 4. They're numbered right there. That number will match that. That's how it works. So we figured out what we want to do. Now we just have to do it. That's the easier part. But is there any question on how we got what we have there? Okay. So let's do 15, choose 12. Okay. What goes in the top?
15 factorial.
And in the bottom?
3 factorial.
Okay. Everything from what number down is going to cancel in the top?
12.
Everything from 12 down is gone. So all you're left with is what?
15, 14, 13.
15, 14, 13. And in the bottom, 3 times 2 times 1. Okay, let's start reducing. What can I reduce?
3 into 15.
Okay, 2 into 14. So I have 35 times 13. Somebody tell me what 35 times 13. How much?
455.
1,255?
450.
Difference between.
Any questions on how we got 35 times 13? Okay, so we got our coefficient. Let's put that down. 455. What's 2x cubed going to turn into?
8x.
No,
Oh, 8x cubed.
8x cubed. So 8x cubed and 3y to the 12th. Well, 3 to the 12th is 531, 441. And what's going to be my y power?
Y.
Y to the 12th. Okay. So when we write the final answer, we usually want the variables next to each other. X cubed, y to the 12th. And in front of that, we need our coefficient, which is 455 times 8 times 531, 441. Okay, so what do we got? 193, 444, 52, 4.
Where did that big number in front of y come from?
3 to a 12.
Which number?
3 to 12. The 5 we were using.
Oh, 531,441, that's 3 to the 12th.
Alright.
Huh. So if we were writing out this entire expansion, that would be the 12th term. Any question on that? Alright, so whatever that comes out to, 1,934,445,204. Okay, and that's 11.2. Okay, so that's homework for tonight, and the different topics that are on the test.
Is it all like what it does?
Yes. So the topics, let's see, from 11.2. So we have series. So things you should know about. Those are the topics that are on the test.
Annalise, can you put your head down?